Now that we've talked about the stability of closed-loop systems and closed-loop transfer functions, now we can move on to some of our other control goals, including tracking and regulation, or disturbance/noise rejection. So these are a couple of our other control goals, and then we'll move on to sensitivity after that. So if we come back to the way that we derive that generic closed-loop transfer function into its three different terms, due to the external reference signal, the external noise signal on the sensor noise, and the external disturbances. The way that we wrote this down is we found these transfer functions and we gave them these names S and T. And so if we're going to put this, if we put this in terms of the tracking error, which remember the tracking error is essentially the reference minus the output Y. So we'd like that error to be small. So in that case, we want S to be small because we want this whole quantity, the whole error to be small. So all of these terms would ideally be small. So we'd like this to be small. We'd like this term to be small because S would make the first term small, T would make the second term small, and then again, if S was relatively small, then this would also make this third term small. One of the things that we observed, though, is that in our generic diagram, this was our closed-loop transfer function S, and this was our closed-loop transfer function that we called T. And so what we observed is that their sum had to be equal to 1. And so again, you just get this by adding, these are common denominators, so you just add the numerator and you just get 1 plus gk over 1 plus gk, which is 1. And so what this is telling you is that there's this kind of fundamental trade-off between being able to do good in terms of tracking, essentially matching that reference, and then the fundamental trade-off is with how well you can reject, for example, some of these noise terms, that sensor noise. So there's this kind of trade-off between doing good in tracking and good in disturbance or noise rejection. So the problem here, or actually not the problem, but the solution here that we're going to see, and we're going to touch on this at the very end of the class, is the fact that if you keep kind of in your mind what these variables are, so this G and this K are transfer functions of the plant and the controller, and these are actually, right, these are G of S and K of S. So these are transfer functions, and the key is that they're functions over S. And what S corresponds to, we're going to interpret it more and more in terms of frequencies. That's particularly true when we look at like the Bode plots and we substitute I omega in for S. So there it gets a little bit more explicit. But in general, the idea is that we're going to essentially change S and T in terms of S. So these S and T are also functions of little s, the Laplace variable. And so that means that what we're going to do is we're going to take advantage of the ability to change the value of S and T when at different values of S. So essentially when S is, for example, small, we could make S small and T relatively large. And then when S is large, then we swap that. And so then that allows us, even though S plus T always has to be equal to 1, that can happen in a variety of different ways depending on what the value of little s is. And so we can design our transfer functions, design our controller transfer functions to make that happen. And one of the things, as you remember in our original discussion, is sensor noise is something that looks very noisy. So this is the kind of signal that we're adding to the sensor, nominal sensor value. In tracking, typically our tracking functions are something relatively smooth and with maybe just a few jumps. So for example, it could step up, or it could just be kind of some sort of function. If you imagine like a quadcopter flying around, then you'd have kind of like some sort of trajectory it's trying to follow in air, but it certainly looks less jumpy than this particular signal. And so what we're going to get appreciation for with one of the labs is being able to understand kind of the fact that this has high frequency content, this noise does. And so that motivates us to essentially make S small at low frequencies. So that means it's good for tracking at low frequencies, and then make T small at high frequencies where the noise is really present. The noise is really present at those high frequencies, so that's when we make T small. So the next thing that we're going to do is we're going to jump into looking at how we do analysis of how well a closed loop system tracks different references. So we're going to motivate this, again, using our favorite example of the spring mass damper. Again, we've kind of gone through this example a couple of times. We started with the differential equation. From there, we get the open loop transfer function, the 1 over ms squared plus bs plus c. We're going to inject a controller into this closed loop system to produce the input into the system. We're going to do that with unit feedback, so there's nothing on this bottom edge. But again, this signal right here is exactly E, which is R minus Y. So that's our tracking error E. And so our controller is going to use that tracking error, essentially stabilize that tracking error. And so we're going to, in this case, we're going to consider proportional control. So that means that our transfer function for our controller is simply just a constant, which we'll call Kp. So if we do that, then what we do is we formulate the closed loop transfer function, that's this. And remember, what this is telling us is that y is equal to this closed loop transfer function times capital U. Or sorry, not capital U, this is important, this is capital R. So with our closed loop transfer function, remember, we're going to replace this whole thing with a single box. And what goes in is R, and what comes out is Y. And so this closed loop transfer function is a transfer function between R and Y. So again, once we simplify this, we get just this as our closed loop transfer function. And so now it becomes interesting what happens if we go ahead and plug this into our error, because that's really a good way to evaluate how well we're doing in our tracking error. So what we're going to do is, right, this is Y, and so we're going to plug that in right here. And so remember, this is going to be this closed loop transfer function multiplied by this the input signal reference. So now it's going to be, to evaluate the error, it's simply just going to be R, the reference, minus this whole quantity, and that includes an R. And so we can factor out the common R and create this as the remaining fraction. Okay, so it's pretty easy to do. You're just going to write this is just going to be R minus this quantity Kp over that denominator times R, and the key is just to get a common denominator and subtract these two quantities together to get this guy. So I'd pause the video if that's not super clear to you, but you get this closed loop transfer function between the reference and the error. So now it becomes interesting is now we can hypothesize different types of references that we may want to follow. So again, these would be the types of functions that we would like the output to mimic. So in this particular example, we're going to consider what happens if the reference essentially is a step function. So it means it was at 0 and then it's going to step up to 1. At t is equal to 0. And so what we're interested in understanding is what is the steady state error. And so we've just said that the reference is going to be a step. So the Laplace transform of the step function is 1 over s. And so this would be an example of, for example, having a car and essentially setting the speed to be some value, 50 miles an hour, and you're starting at rest. And so then it would be the dynamics of the car, the speed of the car as you achieve that 50 mile per hour value. So this notion of getting a steady state, this should kind of remind you of a theorem that we proposed a while ago, which is that final value theorem. And so one of the ways to evaluate the steady state value from a transfer function is, if you recall, we take the limit as s goes to 0 of s times the transfer function. And that's going to give us little e at steady state. So that's going to be little e, this right here, is equal to the limit of e of t. So that's the error signal of t as t goes off to infinity. And remember, little e is just r of t minus y of t. And these are the time domain signals. So we're going to get the final value in the time domain of the error, and we're going to do that from the transfer function. So we're going to use that final value theorem. We saw this in lab 2, and we've seen it way back when we introduced the properties of the Laplace transform. So now what we're going to do is we're going to stick this expression here, because that's our expression of the error transfer function. We're going to stick that into here. So we're going to multiply by this factor of s. This is what we already had, and we're going to replace r with 1 over s. So that's how we get here. And so in this case, it's particularly convenient. This s and this s cancel. And so now we're interested in taking the limit of what remains as s goes to 0. So when s goes to 0, this term goes to 0, this term goes to 0, this constant stays around. This term goes to 0, this term goes to 0, and these two constants stay around. And so that means that the steady state error is going to be c over c plus kp. And so what that says is that if we inject a step in the reference, the closed loop controller that just uses proportional control will yield a constant error in steady state. So that means that your step function, the response due to a step function for this closed loop system will never actually reach 1, but we can make it get really, really close if we make kp super large. And so the way that we would do that is we want to make this steady state error as close to 0 as possible. And so if we make this kp super large, then that's some nominal value for c divided by something that's really big. And so that's the way that we can use proportional control to get a decent result by picking kp relatively large. And that's essentially considered a high gain approach to driving the steady state error of tracking to 0. And so what that means is if you drive that to 0, remember that essentially makes y look like r in steady state, which means that y would be, in this case, since r is a step function, in steady state y would want to be 1. All right, so in the next activity you'll get a chance to do this exact same calculation with proportional plus integral control. So now we're going to change this controller and observe what happens to the steady state error. And so this is starting to understand how different pieces of controllers can help affect our tracking performance. So if you don't understand this activity, I'd pause for a second, go through it carefully before you try the next activity, which again is the exact same thing using proportional and integral control.